Welcome to The Explainer. Today, we're diving into some fantastic source material to conquer a villain we all know a little too well, rigid, brittle code. You know the exact kind I'm talking about, the code that practically shatters the second a new feature is requested. So we're going to unpack the essentials of object-oriented design found in our sources to help you build software that doesn't just survive today, but actually sustains and thrives tomorrow.
It's a question we've all honestly asked ourselves at, 2 a.m.? Why does so much software break when business rules change? You tweak one pricing policy because marketing had a bright idea at 4 p.m. on a Friday, and suddenly, boom, the entire inventory system crashes. It's that universal pain of late-night debugging. And the answer usually lies in how our code's building blocks communicate with one another. If they're all tangled up, every minor change is just a disaster waiting to happen.
So here's our roadmap for this explainer based on the sources. First, the power of interfaces. Second, abstract classes and hierarchies. Third, the inheritance trap. Fourth, contracts and consistent behavior. And finally, mastering solid and dependency. Let's get right into it. Starting off with Section 1, the power of interfaces.
When the texts talk about fragility, they're usually pointing a big red arrow at tight coupling. Just imagine hard-coding your business logic, like a massive multi-branched if-else statement to calculate product pricing based on every single item type. If you program directly to that concrete implementation, your high-level system becomes incredibly vulnerable. Every time shipping changes their rates, you gotta go digging into that monolithic code block. It just creates rigid, brittle code that eventually shatters under the weight of inevitable change.
The absolute core takeaway from the text is this mantra right here. Program to an interface, not to an implementation. If you remember just one thing from this explainer, let it be this. By relying on an interface, you create a beautiful separation between the use of an operation and its actual implementation. You're effectively shielding your high-level code modules from the absolute chaos of low-level changes. Take a look at this. We have an order system that needs to look up customer info. But instead of wiring it directly to a specific database, it connects through a customer lookup interface. This enables what we call lazy object creation. At runtime, this system can seamlessly connect to an in-person store implementation or an online web store. The high-level order system doesn't have to change a single line of code. It honestly doesn't care how the data is fetched, only that the interface's contract is fulfilled.
Moving right along to Section 2, abstract classes and hierarchies.
The source material uses the Java collection framework to brilliantly illustrate the bridge between pure abstraction and concrete details. Notice these classes sitting right in the middle, like abstract list or abstract queue. They act as this intermediate layer. They provide a shared codebase, stuff that every list needs so you don't have to rewrite it from scratch, but without exposing all those gritty implementation details to the end user.
Now, abstract classes give us some massive strategic benefits. They support code reuse across large structural hierarchies, and they're fantastic for providing application frameworks, where you have a generic control flow, but you want subclasses to fill in the specific steps. But the sources do offer a quick warning here. If you rely on abstract classes purely as data types, especially if they implement multiple mixed operations, it can lead to some pretty messy, unintentional misuses. Think of them as a transition tool, not necessarily the final destination for typing your objects.
Which brings us to Section 3. The inheritance trap. Okay, we actually have to unlearn something here because our intuition about real-world concepts doesn't always cleanly translate to code. In math, sure, a square is a rectangle. But if you force a square class to inherit from a rectangle class, you're absolutely going to break your architecture. Why? Well, a rectangle allows its width and height to be modified independently. If you do that to a square, it's not a square anymore. You end up having to artificially restrict the parent's behavior in the child class, and that just causes rigid dependencies and completely unpredictable bugs. To avoid that trap, the sources draw a really critical comparison. When we want to reuse code, we often just default to inheritance, which is known as white box reuse. The problem with that? It exposes all the parent's operations to the client, even the ones you really don't want them touching. The smarter alternative highlighted in the text is object aggregation, or black box reuse. Instead of saying Class A is a Class B, we say Class A has a Class B. You safely encapsulate the functionality and completely hide all those unused properties. Honestly, choosing aggregation over inheritance is like finally untangling your headphones before putting them in your pocket. It directly prevents your future code from becoming a fragile mess. It eliminates rigid class dependencies, it hides dangerous unused properties, allows you to swap out objects at runtime, and just massively reduces the overall complexity of your modules. It's a total game changer for sustainable code.
All right, Section 4, Contracts and Consistent Behavior.
This is where the rubber really meets the road. The Liskov substitution principle. It formally states that if S is a subtype of T, objects of type T can be replaced with objects of type S without altering the correctness of your program. Think of it like a strict business contract. If a parent class promises to deliver a specific outcome, any child class substituting for it must honor those exact same behavioral promises. No surprises, no random crashes.
This builds into the much broader metaphor of design by contract. As you can see, software elements collaborate based on mutual obligations. You have inputs with strict preconditions, meaning what the module expects. You have the execution, dealing with errors and exceptions. And you have the outputs with postconditions, what the module guarantees to deliver. It is exactly like a supplier and a consumer in the business world interacting.
Practically speaking, this logic, which is rooted in Hauer's logic, means the rules are basically set in stone when you're overriding a method. You can't suddenly demand more from the caller, so preconditions cannot be strengthened. And you can't deliver less than you promised, so postconditions cannot be weakened. If you strictly maintain this, your system remains infinitely reliable. Finally, Section 5, Mastering Solid and Dependency. These 5 principles right here are the absolute gold standard for object-oriented design. Single responsibility, open-closed, Liskov substitution, interface segregation, and dependency inversion. Now, the open-close principle, that's really our overarching philosophical goal here. Making our code open for extension, but completely closed for modification, meaning we can just add new features all day long without ever risking breaking the existing tested code. And how do we actually achieve that? Through dependency inversion. High-level modules should not depend on low-level modules. Both absolutely must depend on abstractions. This circles right back to that core mantra from earlier. Relying on abstractions, like those interfaces we talked about, prevents your core application features from breaking just because a low-level business rule, like a database query or some UI component, fundamentally changes. In practice, dependency injection utilizes a broker. You have a client and you have a service, but they never directly connect. Instead, the injector wires up the abstract dependencies at runtime. The client just asks for a service that fulfills a specific interface, and the injector provides it. The client never has to care or even know about the service's concrete implementation. It is 100% decoupled. Which leaves us with this final, somewhat provocative thought to take back to your own desks today. Look at the projects you're currently working on. Is your code genuinely open for extension, but truly closed for modification? If the business requirements totally change tomorrow morning, are you going to be writing a quick new implementation, or are you rewriting your entire core system? By leveraging the sustainable architecture tools we highlighted from the sources today, you really can build software that lasts. Thanks for exploring this explainer with me. So, how will you apply these principles to your code base tomorrow?